Welcome here, everybody, to today's seminar. Today we have a visitor from India, Debabrota Basu. He had his PhD from National University of Singapore, and he's been doing a postdoc at Chalmers in Gothenburg, and he's now faculty at India in Lille. He works in statistics, machine learning, optimization, and the topic today is about uncertainty quantification and its applications in reinforcement learning. So please, Deba, the floor is yours.
Okay, so thank you, Olaf, and thank you everyone in RISE for inviting me to talk about this exciting new research that we have just recently submitted. And this is a joint work with Hannes and Christos Dimitrakakis from Chalmers University of Technology. And we'll talk about it and we'll see like what is in there. So as you can see, the heading or the title of the talk, it is called Sentinel, the method we have developed, and it contains mainly two components. One is quantifying the composite uncertainty, and the other one is its application in risk-sensitive reinforcement learning. And yeah, obviously, as Olaf has introduced, I am Debabrota and Debabrota Basu from INRIA School. So it is a team in INRIA Lille, and I'm going to talk today. I'll stop my video just to get the internet properly so that you can hear me. So, okay. So we can start now. So Sentinel, as I have already said, includes mainly two components. One is quantifying the composite uncertainty, basically uncertainty in decision making. And the other one is its application in risk-sensitive reinforcement learning. So the talk consists of mainly four parts. One is decision making with uncertainty, which is in general what reinforcement learning is all about. And then we'll talk about what are the sources of uncertainty. Basically, the two sources of uncertainty in reinforcement learning that we are interested in, the epistemic and aleatory uncertainty, and then a bunch of risks, like how you can quantify coherently this uncertainty, how you can like find out a risk measure that can actually represent them and quantify them. And then once we can represent our corresponding uncertainties, the next goal is obviously how we can use it for decision making. And there comes our algorithm framework, Sentinel. So to start with, what is decision making? How does a decision making under incomplete information look like? Let us consider a human being who has like the amount of certain health conditions, like whether the person has fever, high pressure or low pressure, what are the respiratory condition and all this. So if we consider all these features together, that is a representation of the medical state of this person. And as this medical state of this person is given, now the decision problem to a doctor becomes like this, that, okay, if there are capital A number of medicines and there is a Dr. Pi, don't mix it up with the movie called Dr. Pi, but yeah. So there is a Dr. Pi, which is basically an algorithm that chooses a medicine. And then if it chooses the medicine A1, the person goes to a medical state, say S1. And if it chooses another medicine, say A2, it goes to S2 and so on. And then the next part is the doctor watches or observes some kind of improvement, R1 to RA, possibly for applying each of these medicines on the person. Now, what happens? Basically, the person is presently at a medical state ST, and it goes to a medical state ST plus 1. And this is decided by something called a transition distribution. We model it using something called a transition distribution, which is unknown to us, but there is one underlying. So we assume that. And there is this improvement, we call it reward typically in reinforcement learning jargon, and there is a reward distribution that dictates what will be the corresponding improvement of the person. And how does a reinforcement learning problem, or typically called the Markov decision process, look like? So then the doctor can choose up to capital T number of medicines in sequence after observing the patient's condition. And the goal of the doctor, or here the algorithm, is to choose medicines at every step such that it maximizes the total improvement of the patient. That is sum of this RTs, where T goes from 1 to capital T. So given this horizon, given this time horizon, the doctor has to improve or wants to improve the medical condition of the patient as much as possible. Decision making depends on two main criteria. One is this incomplete information, because the doctor doesn't know two things. The doctor doesn't know how are the reward distributions, how the patient is going to improve, and what are the medical states that patient is going to be after applying the medicine. So the doctor doesn't know the transition, and the doctor still has to optimize the decisions of medicines depending on the observations it gets. So this has these two components. And today, we are mainly interested in how are these uncertainties can be represented and quantified. So before going into that, we'll talk about the model just a bit more formally. So this model is, as most of us know, is called the Markov decision process. And the Markov decision process is actually a model of iterative decision making, because doing maths, we need to make models to make them tractable or do something on them or design algorithms. And this model can be represented using this thing. One is a state space, basically the medical states of the corresponding person, which can be anything in a d-dimensional real space. An action space, basically the choices of medicines, which can vary from 1 to A, or like in some of the cases, if you're driving a car or etc., it can be a real value, basically. But let us consider it can go from 1 to A. Depending on that, we call it discrete or continuous action space. And there is a transition kernel. So if one action is taken, depending on a state, then with certain probability, the person goes to a next state. We transit to the next state. And this delta represents the probability distributions over S, probability simplex over the state space. So that dictates with what probability you can go to one of the next states. And what is the reward function? That is the one quantifying the possible improvements of your depending on your decision. So if you have, if you are in a state S, take an action A, then you get a corresponding reward value that says, okay, how good or bad your decision was. And now, what is the goal of this reinforcement learning thing altogether? The aim of doing reinforcement learning, and in reality, we don't know the MDP, we can only access it. So in an unknown MDP is computing a policy pi that maximizes the expected cumulative reward over a time horizon T. So that is very important, that in classical RL, we try to improve the expected cumulative reward in these cases. So the expectation point is very important, and we will see why we are saying so. And if we look into this expectation is dependent on not only the policy, but also the MDP, but the MDP is not known to the doctor or to the algorithm. And this is the total cumulative reward given the patient started from an initial state. So this is the thing that we often try to improve. And I'll just throw some jargons that people often use in reinforcement learning, just for the ease of referring them later in the talk, that this expectation is called the value function of the corresponding policy pi. And this thing, that is the cumulative reward, this thing inside expectation, this total sum of rewards, that is often called the return of this policy pi. And we take its expectation depending on the uncertainty of the policy and depending on the uncertainty of the MDP. So there are two factors in there. So you may ask, like, okay, given the MDP, okay, I can calculate this part, obviously. And given a deterministic policy, I can calculate this part, obviously. Yes, you can do, but we have to remember that we don't know the MDP. And from that point, this part becomes important, that is not knowing the mu. And from the other point, that your decision can be a bit probabilistic. You can take rather than taking a deterministic decision that, okay, if I observe this, I will take this decision. You often take it randomly. Like there is some inherent randomness in that. So these are the mainly two sources of randomness that we will see later that we are interested in. So basically, to summarize reinforcement learning, we try to maximize the value function, which is expectation of return, depending on a policy phi, where the MDP is unknown. And I think most of the people who have seen any reinforcement learning lecture or talk, like this is the favorite picture that comes up in the first slide, but I wanted to delay it a bit. So this is typically the framework or the flowchart of reinforcement learning, iterative reinforcement learning as we have seen it. So there is this agent or the algorithm that takes an action and it interacts with the environment. That interacts with the environment, or often called the MDP, and observes something out of it, that is the reward, and the next state, whatever state the person goes to. And the reinforcement learning aims to solve the sequential decision making, just to remind us ourselves again, under incomplete information, and that is the main point of interest for this talk, while interacting with the environment and representing the corresponding uncertainty, because we cannot design an algorithm till we have a proper representation of this uncertainty. And then once we have that, we optimize a long-term goal, which is like optimizing the value function, which is expectation of the whole return over time horizon T. So this is in brief reinforcement learning, and that we are going to talk about. So just 3 words I like to summarize the whole thing. If it is too long, the explanation. One is adaptive interaction with an entity. One is a representation of uncertainty. And once you represent it, you sequentially optimize it. These are the main 3 components of any reinforcement learning algorithm. And today we are going to talk about mainly this point that is of our interest, as you have seen from the title of the talk. So as we have already said that we want to quantify uncertainties, first we want to look into what are the sources of uncertainty, from where these uncertainties come from. So there are 2 sources, and we'll talk about how do they interact. So if we look into again, what we wanted to optimize is this thing, right? This expectation over return. And this expectation of over return depends on 2 things. One is this MDP, another one is this policy. Now, this MDP is unknown. So there is some uncertainty due to the lack of knowledge about the truth. So even if we think the decision making in real life, if we don't know how the reality is, or if we cannot model it correctly, there is some uncertainty regarding that. And this is the uncertainty due to the lack of knowledge. And the other one is the inherent randomness of real life. So the transitions or the rewards, as we have said for MDP, our MDP model, they are stochastic. They are random. They are not deterministic. It is not like you take decision A from this state and you get the best answer or the worst answer. So due to that, we see there are 2 types of uncertainty, and the typical name of them are epistemic uncertainty, the uncertainty due to the lack of knowledge, and the inherent randomness, also the aleatory uncertainty. So these are the basically 2 uncertainties or 2 sources of them that we are interested about. So let us take a simple example. Let us consider we have a random mixture of Gaussian, and there is something, some random variable Z1 coming from this distribution N with mean -1 and standard deviation 1. And there is this Z2 that has mean 1 and standard deviation 1. And the one of Z2 is in the color red, and the one of Z1 is in color blue. Okay, so now we want to see how do the mix. So if we have some weight omega on each one of them, and we create a new variable, so Z, by mixing them, such that Z is basically omega Z1 plus 1 minus omega Z2. So in this case, we observe if the omega is a quantity that is also random, that is also unknown, and comes from a beta distribution, then the corresponding distribution of Z is not exactly this distribution or addition of them, rather a marginal, which can be quite different from this individual 2 distributions like this, that comes from this mixture. So the distribution of the Z becomes quite a bit different than the Z1 and Z2. And why this is happening? Because this omega that is corresponding to here, that is also uncertain. And if we look into it, that exactly this simple example exactly shows us what is the problem. The mixture of Gaussians corresponds to the aleatory uncertainty of Z. So since Z is a mixture of this n-11 and n11, so we cannot ever avoid this uncertainty because it is coming from these two Gaussians. But there is another one, because we don't know omega and we are assumed that omega is coming from a beta distribution. There is another set of uncertainty on this weight omega that is coming from this corresponding beta distribution, and that is exactly the source of epistemic uncertainty of Z. So that's how, from this simple example, we start to see that there is this random mixture of Gaussians and how we can observe epistemic and aleatory uncertainties in this. So given this uncertainties, obviously, as practitioners of machine learning or statistics, our goal is to obviously estimate them. And there are one good news and one bad news. So the good news is that this epistemic uncertainty is coming from the lack of model. But as we can generate more, almost infinite data from the true model, the epistemic uncertainty goes away. Because right now, you know that it is not a beta distribution or whatever you assumed initially about omega, but you know the exact value of omega because we have collected enough data from the true model. But the problem is this aleatory uncertainty, which is coming from the underlying two Gaussians, you can never get rid of them. So they will be always there, even if you are going to use a deterministic policy, like if your omega is fixed, deterministic, it is not random at all, your Z is still going to have this inherent randomness. And these are the typical asymptotic properties of epistemic and aleatory uncertainty. But now, how do they interact? That was not very clear, or that is not very clear still in the community, and we wanted to understand that. So the question is, what happens if the data is finite? If you don't have access to infinite data, which is reality. And so if the planning horizon is finite, so if the T is finite by the time of your decision making, you can never have access to infinite data. So how we are going to make decisions under these two uncertainties? And how do these two uncertainties get tangled in this finite data? So for this purpose, we proposed our framework, Sentinel, that comes with this idea of composite uncertainty and how we can compose these two uncertainties and understand non-asymptotically, because in finite time with finite data, how these two uncertainties react or interact. So yeah, so given this, I will go to the other part, that is the risk measures, a bunch of risks that we are going to talk about, and how we can quantify these uncertainties coherently. Is it fine till this? Is there any doubt, anyone? So that I can move to the next part. If there's any question.
Deba, there is a question. There's a question in the chat. For epistemic uncertainty, couldn't you actually split it into two possible sources? One is uncertainty in your approximator, the other being partial observability, which I couldn't really call aleatory.
Yeah, so thank you for the question, Jesper. Allegoric or aleatory? Okay, yeah. So,
I think it means aleatory.
Yeah, so yeah. So now, in this case, I think that's a good question. The uncertainty of the approximator is obviously there. The other case is the partial observability, right? So we are saying even if your approximator is completely correct, still you are going to have this epistemic uncertainty because you have this partial observability about the model. You don't know the model completely. And that is the source of epistemic uncertainty here as we are considering. Then if your approximator has some errors and etc., then that will be added to that. But that is not the natural source, or that is not, that is something that is a creation of your algorithm that is even without that, we are going to have the epistemic uncertainty. So yeah, I hope that answers your question. So, okay. So, okay, thank you. So then I'll move to the next part. The next part is how to quantify these uncertainties and how to coherently quantify these uncertainties. So when we try to quantify the uncertainties, typically we talk about the risk measure. So what is a risk measure given a random variable z? So a risk measure takes a random variable z coming from a certain distribution, say B, and then maps it to a corresponding real value. And this risk quantifies the probability of occurrence of an event away from the expected value of the distribution. So if we take this example, here we see that this is the expectation. This is a standard Gaussian with 0 mean and variance 1. And then its expectation is exactly at 0, right? And then we want to know with how much probability an event occurs that z is less than equal to alpha. Or we want to know how much is the probability that z is greater than equal to alpha. Because it may happen that you are designing an algorithm, and typically most of the stuff are designed around the expectation, but that z goes in reality far away from the expectation, and so that you cannot handle the consequences of it or effects of it. For example, if you design a automated car that only depends on the expectation and doesn't care about this kind of tail bounds or tail events far away from the expectation, it may just cause into mishaps, and still the expectation will be good enough. But we don't want that in real life. So we want these risk measures to quantify the probability of occurrence of these events, like what is the probability of z being less than equal to alpha, or what is the probability of z being greater than equal to alpha, something like that, which is far away from the expectation. And one of these examples is conditional value at risk, which is pretty much used in decision making, finance, and other operation research and other places. And what CVAR quantifies? CVAR always comes with a parameter alpha for sure, and a CVAR alpha quantifies the expectation of the worst alpha % of a probability distribution. So if we take, for example, the left tail as the worst tail, and if we take the alpha % of it, the CVAR quantifies what is the expected value in this alpha part of the tail. So if we look into this alpha part of the tail, that is the lower alpha %. So what is the expected value for the lower alpha % of the tail? That is exactly the CVAR alpha. And this is what typically the risk, one of the examples how risk measures quantify uncertainty. But yeah, you may ask so then expectation is not a risk measure. It is also a risk measure. It doesn't just quantifies how close you are to expectation itself. So yeah, it is a redundant, or you don't care about such a risk measure. You want to have something more sane. And if you want to have something more sane, people have tried to look into what are the coherent risk measures, what are the risk measures that make sense. And interestingly, till 2001, we didn't have a proper categorization, even mathematically, for that in most of the cases. And then Arstner et al., they came up with this coherent risk measure idea that said a risk measure that is coherent has to satisfy these 4 properties. What are these 4 properties? One is monotonicity. If a random variable x is less than equal to y, then its risk is obviously less than equal to risk of y. And which makes sense. If a variable is always less than another one, its risk is lower. Then there is this positive homogeneity. You don't want that you multiply x with 2 and the risk gets non-linearly multiplied. You want basically risk of cx to be c of risk of x. Typically, we like linear stuff. And then translation invariance, if you add a constant that has nothing to do with x, then just that constant gets out of your way. So basically, these are typical linearity properties that we like. And this is the monotonicity property, that it is always increasing, at least non-decreasing. And the other point is if you add 2 variables, then risk of this sum of x and y is always less than equal to risk of x plus risk of y. Why? Because when you are adding two variables, you are not only adding them, you are coupling their uncertainties, and coupling their uncertainties may have consequential effects. So you want a risk measure that takes care of that. That doesn't add them equal or less. That says like, okay, I can take care of this coupling property. And that's why like risk of x plus y is less than equal to risk of x plus risk of y. And if we look into this property, there are very interesting and traditionally available risk measures that people have used, can be divided into two parts, coherent risk and incoherent risk. For example, CVAR is a coherent risk, but VAR, that is called value at risk, which has been used quite a bit till 2001, and also still it is used quite a bit in finance, is incoherent. So people have shifted to this from VAR. For example, variance, that is often used in reinforcement learning literature for risk, is not coherent, but standard deviation is coherent. The other point is like people use exponential utility. You see most of the risk-based MDPs or reinforcement learning initially are dependent on exponential utility. Even in control, process control, you will see lots of use of exponential utility, but it is not coherent. Rather, what is coherent is its var counterpart called entropic var. And also historically, we have seen people shifted to this. Similarly, we can see for expectiles, people who are interested in distributional reinforcement learning specifically, they've heard this term. That is not actually coherent, but Wang risk measure, a normalized version of this, is coherent. So, it says like we should move to this part of our table rather than staying at this part where we have seen lots of historical research and like lots of things that have been done in research community. So given this, we know what kind of risk measures we want to use for our purpose, but there's something more. You don't want to use only risk measure, as Jesper has asked, like one is the uncertainty of my approximator. My approximator also will have some error because of the finite data. So then I want a proper estimator that can estimate these uncertainties well. And then there are certain set of uncertainties for which the estimation can go really clean. And we'll focus mainly on them. They are called the spectral risk measures. What are the spectral risk measures? So that says like if under one random variable x, the probability of occurrence of one event E1 is greater than probability of occurrence of another event E2, then for another random variable y, that should happen same. So if for xe1 is greater than xe2, then ye1 should be greater than ye2, and vice versa. So basically, if x and y change similarly, depending on same set of events, they are called comonotonic. And if they are comonotonic, adding them should not yield any problem. There is no need of subadditivity anymore. This is a technical issue, but I am not going into that. But that makes sense because if there are two random variables that behave similarly or that weigh similarly to events, then their corresponding risks should be similar. That helps us a lot in estimation. And the other thing is like if the two random variable has two CDFs, fx and fy, then their risks are same. If fx equal to fy, their risks are same, because we will see again all the estimators of risks mostly depend on the CDF and use it. So if the CDFs are same, if we get the same risk, then that is good for our estimation. And if this happens, we see that there is always a utility function, and we can come to our traditional, like comfort zone of decision making, that there is something called a distorted utility function, so that you can write this field as like not only integration of z, but a distorted CDF that is u composed on p, basically. So we know for expectation, we always write it like integration of z dp, but in case of risk, this is exactly just this change. You change your weigh your events a bit differently depending on a distorted utility function. It distorts your corresponding density function. And you can equivalently write it like this with some change of variable in integration. You just see that you can still integrate over z, but if you put inside the utility function your CDF, 1 minus your CDF, then you are done. So basically you can use your CDF to calculate your corresponding risk function. And we wanted that. We wanted an estimator that is very clean and easy to calculate. So basically, if you can calculate the CDF well, you can calculate the risk well. And we know that for CVAR and most of the commonly used coherent risk, we can get such a U. For example, for CVAR, it is just a minimum of T divided by alpha or 1. So basically, it looks something like this. That if you have the axis up to here, then for this x-axis being T, there's some software issue. Please hold on a bit. Okay, yeah. If the x-axis is T, then the CVAR, this U alpha varies like this exactly till a point where it is alpha, and after that it becomes exactly 1. So it is like a step function, a modified step function. So that is the distortion you do. Basically, you go linearly up till the P is less than or equal to alpha, and then you make it 1. So rather than taking this linear thing that we take for expectation, you change it to this. And that is the exact distortion that we are talking about. And doing this simply gives you this estimator that you can calculate your PDF, put this distortion on that, do the integration, you are done, you get the risk measure. And just to go into this, how you can derive and how we have derived a proper estimator, a distribution-free estimator of the risk, that you just take the thing that you are interested in, say random variable Z, you make a histogram of it. Then using the histogram, you compute the corresponding quantiles. We know that we can calculate percentiles and quantiles on histograms. And then for each bin of the histogram, you multiply this with the corresponding U alpha I, which is basically, you can think of like the left value of the bin, and you multiply this with U prime alpha I and add over it multiple alpha I. So like if your range is say from 0 to 1, and you have defined multiple alpha I and calculated each quantile value at this and each U prime alpha I in here, you just multiply them, sum them, you get a proper estimate of your risk. And it becomes really simple without a complicated estimator. You don't need a distribution for this. So that's how we have made a proper estimator of risk, and we are interested to use this for all the good algorithmic purposes. So now given this, we can define the aleatory risk simply like this, that aleatory risk is the deviation of total risk of individual models. Once. Yeah, individual models, say Z given theta, with respect to the average model, let's call it Z hat. So how much my uncertainty of or risk of the individual model Z given theta varies from the average model. That is exactly the aleatory risk, and you can define it like that. And then how you can define the epistemic risk? You can define it like the risk of the random variable Z still, but depending on the distribution beta over the model. So you can see really the difference. We have applied the distortion here over beta. Here we have applied the distortion over Z. And that says like the part of that source of uncertainty that we are interested in. And this formulation really allows us to decouple all these things and still use them properly or separately. Anyway, so this, though this may seem a bit, full of equations and jargons, we can visualize them very easily. So how we have seen them before, like we have considered there is a Z1 coming from a normal distribution of -1, 1. And there is a Z2 coming from this distribution in 1, 1. And now we wanted to mix them with a weight that is coming from beta distribution. How do the marginal look like? We have seen that the marginal look like this black line, right? And in this case, we can see the expectation of this joint thing is still here because the expectation works like normally, linearly. This is the expectation of this whole black distribution. And then there is this aleatory uncertainty that we can calculate, which is basically the uncertainty of Z1 and uncertainty of this mixture of Z1 and Z2. So this is the uncertainty that we are interested in while averaging out the uncertainty due to omega. And other case, we want to calculate the epistemic uncertainty, where we are interested in the uncertainty of omega and 1 minus omega, while averaging out the uncertainty of Z1 and Z2. So we see that there are these two types of uncertainty, and they are two different uncertainties. So just to summarize, in one case, we average out omega and 1 minus omega and take the uncertainty over Z1 and Z2. In another case, we average out Z1 and Z2 and take uncertainty over omega and 1 minus omega. That's the main difference. Now the question that we have started from, how we can handle them, when they are mixed together. And for that, we have defined this composite risk. And this composite risk comes naturally now from this definition of spectral risk, that if you have one aleatory risk, UA, and if you have another one, UE, for epistemic risk, then apply them on the corresponding distribution. That is the distribution of each model. You apply UA, and the distribution over models, that is the beta, for that you apply UE, and then you integrate them. And okay, like that's the answer. That is the composite risk, exactly. And why this is interesting, like what's the benefit? First thing, it is coherent. If both your risks that you have used, say for example, both of them are CVAR, then this CVAR composite on CVAR is coherent. It will give you the coherent estimate. If now you have a good estimator or a distorted utility function for this aleatory and epistemic risk, you can always use the quantiles of each model and quantiles of the belief distribution to make an exact unbiased estimator and distribution C estimator above that for this risk measure, this composite risk. And another one is the accuracy. Till now in literature, at least as we have seen, people have used mostly additive risk. They have calculated epistemic risk, they have calculated aleatory risk, and they have then just added them. But we have found out this composite risk is always more accurate, and accurate obviously with respect to data. You can ask what is accuracy, what does accuracy mean? Accurate with respect to the data than existing additive risk. And again, we can visualize that for our small mixture of Gaussian experiment. We see that this was aleatory, this was epistemic. If you add them, you get this line, basically this line in here. And if you compose them, you get even a lower value that is more and more close to the data, because lower values talk about, so if you add them and if you see a higher value, that means you are underestimating the risk. If you see a lower value, like the composition, then you are actually estimating the risk properly. Taking it higher actually can make bad decision or lead to bad decision in here. And we see from data, if you make this 100 Gaussians and add them, we see from data that actually we are much closer to the data, that is this blue line, and green line is the composite risk, then the additive risk, which is specifically in these low zones, which are quite further in the tail, is quite far away than the data, is quite inaccurate. And I'll not talk about the next part. So then we'll move to the next part, that is exactly how we can use this composite risk for decision making and how we are doing that in Sentinel. So now we have, if we remember that for classical RL, we wanted to just maximize the value function over return, that is the traditional RL, depending on the expectation. But this is not enough. If we consider there is an MDP with 3 states and 2 actions in it, this simple MDP, as we can see, okay. And we consider a bit more that the 2 distributions we have talked about, like this reward distribution of this state S1 is this, and reward distribution of state S2 is this, okay. Then we see one interesting phenomenon. What is the phenomenon? That if we take an action A1 and always go to this state S1, okay, and never go to state S2, and if we take another action A2 and sometimes we go to S2, sometimes we go to S1, with probability exactly half, as we can see. In that case, we see the return distributions can be of 2 types. So the return distribution for taking action A1 from S0 is like this, and return distribution of taking action A0 from S0 is like this. And if you look into it carefully, you see the expectation of both these distributions are just the same. And still, and that means like if you use traditional reinforcement learning, they will consider you can take each of the actions equally optimally. They are equal optimal actions. But if you consider race, you see that this CVAR of this thing, of this A0, A1 is less than the CVAR of this. So actually, if you look into it, like I think I can use the, yeah. If you see that this thing is a bit lower than the other one, I think due to the axis, it is a bit hard to see, but yeah, we can see that there is a difference between A0 and A1. And if we want to minimize the rate, this is the more optimal action. A1 is the more optimal action than A0. So if we want to be considerate about risk, we cannot use expected value anymore. Rather, we have to have the composite total risk on the return, and then a policy that tries to minimize that. So then we see if this is the return, if this is the distribution of MDP, we have to calculate a composite risk on that and try to minimize. And from this point, we needed an estimator, obviously, that can do that. And what we have done, we have developed Sentinel for that. So what Sentinel does, Sentinel, as usual, like reinforcement learning algorithm, take an action, AT, depending on something, say like Q learning, okay? And then observe the action, then observe the state. And depending on the state, it tries to use different CDQ events, the distribution, return distribution estimators, K return distribution estimators, to get K estimates of the corresponding return distribution. And these are, say, like the K estimates. And then using that, it calculates K values of aleatory uncertainty, and then use this K values of aleatory uncertainty to compute the composite risk, and send this composite risk to the corresponding action selection. And then it carries on. And to start this or to do this, we needed some amount of data, obviously, already to make this initial like constructions of this return distribution. This is something like your reserve data for that. And then as you observe more, you keep on adding this new states and new rewards to your reserve data to update your estimates of the return distribution. And this is it. Like, this is the estimator that we are going to use. It is distribution free. It is completely frequentist, and it just uses something standard in distributional Q learning, distributional reinforcement learning, that is CDQ, basically a categorical or histogram estimate of the return distribution, nothing more complicated or parametric than that. And using that, we start to observe this, that as the number of samples was initially 0, we started with uniform distributions for both of the actions. As you can see, they're all uniform distributions in here, but actual reward distributions were like the blue ones. We have seen that in the example. If you now increase the number of samples to 1,000, the estimate becomes more and more close, but there are still errors, right? And if you now make the number of samples 10,000, then actually we see that Sentinel kind of correctly estimates this return distribution. And saying that actually ensembling quite a bit erroneous approximators, return distribution approximators, CDQ altogether, gives us a proper estimate of the return distribution. And we see how good does this work. Like, we see the Weierstein distance between already known analytical distribution of Z A1 and Z A2. And we observe that our estimations go pretty fast, almost below the error level of 0.001 by the time we reach almost 1,000 or 10,000 samples. Whereas the other distributional estimators, for example, VDQ, that assumes something like a multivariate Gaussian, due to their assumptions and due to their specificity, they stay quite a bit away. Even though actually we are trying to estimate one Gaussian and one like mixture of Gaussians, still they are quite a bit far away due to their assumptions and structures that they need. And then what does it lead to? We have promised that this is going to help us in risk sensitive decision making. And the one thing that people in reinforcement learning are interested in, whether it converges or not. And we observed actually, yeah, it converges. And if we see even the risk neutral version of Sentinel, we observed that this was the initial return distribution for a given policy at time step 0. And then we have kept on updating the policy at each step. We observe the return has increased, and the return has increased, and we are almost converging near one optimal return distribution. So if you want to observe it, you can, like how typically you observe the convergence curve in reinforcement learning literature, it will look like this basically. And for risk sensitive one, we observe that we are also converging, like you can see a convergence of movement from there to here, but still the convergence almost comes near this point after this 30th like update, and which has been obtained for the risk neutral one, almost at 10th or 20th one. But we see another interesting phenomenon. If you see the return distribution in here, that almost spreads from 200 to 500. But if you see in here, the spread is quite constrained, and that is between 100 to 300. So if you see the spread here almost was around 300, where it is restricted to 200 with even shorter barcodes, whereas the barcodes here were quite wide. That says like we are converging to the return distributions, which are not only converging in expectation, but also converging in these tails, which is very essential for the risk, because we are seeing in risk, we cannot afford bigger tails. And last but not the least, like what do we want to do? Like because we want to have something scalable that works something for near to real life application. So we have tried to apply it something on a highway. There is an environment, a simulating environment called highway, which has been made by one of the PhD students in school. And actually, this is a continuous problem where you have to drive a car in a fast moving highway with multiple lanes among 10 other cars. And we have seen that typical algorithms like the VDQN or CDQN, or even the VDQN, if you add risk to it, or there are this existing additive risk formulation, they work much worse than the Sentinel that uses the composite risk. And we observe that we achieve much more value of value function than them. We achieve that we have better estimate, higher estimate of the aleatory metric from them. And obviously the main thing that we crash less, we do less number of accidents, and significantly less number than the typical CDQN or VDQN that we had before. Like it goes down almost pretty much. And for the last one, that is our competitor, that is UADQN, which has almost 1060, we have almost 341. So we decrease almost 3 times the number of crashes, which is, I think, pretty good. 3 times number of crashes is fine. And yeah, that's it. Because last slide, always as we like to conclude in our talk, like our methods work. So we have already concluded that. But if it was too long and didn't listen, so what is the summary? The summary is like mainly 2 components. One is composite risk, one is Sentinel. And how do we get in there? There is this reinforcement learning problem that we are interested in. That is basically sequential decision making under uncertainty. In that case, we observe there are 2 sources of uncertainty: epistemic uncertainty and aleatory one. One is due to lack of knowledge. Another one is due to the inherent randomness of the decision making process, of the real decision making process. Then we join them together in a composite risk formulation. And this is the composite risk. And we say like why we have to be coherent to get a proper estimate to make sense out of this risk. And then we propose SENTINEL-K, which is a risk sensitive, like reinforcement learning component that has mainly this new component that is the estimator that uses K CDQNs to estimate K return distribution, computes K aleatory risk out of this K return distribution, and then compose this K aleatory risk with the epistemic risk, weigh them with epistemic risk to get finally a composite risk measure. And then use it in risk sensitive reinforcement learning, as we have seen, like we have used just Q learning on this composite risk estimate, and which is very traditional, right? And then even with that, we get good performance, and you can see that, yeah, Sentinel acts safe. So our whole purpose of proposing this, that a proper estimate, a proper quantification of uncertainty and proper estimation of that will lead to safer decision-making process, is kind of almost near to be achieved. So yeah, that's it from my side. Yeah, any question, anything that you would like to ask?
Thank you, Debabrota. Do we have some questions from the audience? Really nice. Too long didn't listen slide here.
I can ask a few questions.
Yeah,
if nobody else wants to jump in. So if you go back to the slides with the convergence of the policies.
Yeah.
This one, yes. So on the risk sensitive, it looks like for policy 40 there that the expected return is actually lower than for policy 30. So does that mean that the model is actually diverging, or am I interpreting the graph incorrectly?
Mm-hmm. No, I think that's a good question. So if we look into this return that we are calculating, so typically what we expect, if you add risk sensitivity and if your reward doesn't take care of anything that is accidental or crashes like that, in those cases it may happen that basically n-chain is a normal environment that was designed to work for expected reinforcement learning with expected value. So in that case, if you are going to use this, you are typically going to get less expected value because you are going to be risk sensitive. So you are going to be conservative than unlike the risk neutral one, right? So that obviously most of the time, if our reward is not specifically designed to consider crashes or accidents or fall, is going to be less than the corresponding risk neutral one.
Okay. And another question, if nobody wants to jump in between, is have you considered, I'm just thinking loosely here, but have you considered actually applying this on something like uncertainty-based exploration? Because I think oftentimes those models tend to not work very well when you have a lot of uncertainty in the environment. So if you can somehow separate the uncertainty between the model and the environment, maybe they will work better.
I think that's a good question and good suggestion. I will say we haven't tried, honestly, but what I personally think that this can be done, because our main component, as you can see in here, is this estimation of the composite risk and the better estimation and better quantification of risk altogether. And this can be used, as we have seen in literature before, not only to avert risk, as we have used it already, but also to seek exploration, go risk seeking. I think that will be one interesting application to look for, but honestly, we haven't done that.
Okay, thank you.
Yeah, thank you for the question.
Did you evaluate this on any other tasks?
For now, we have evaluated it only on we have evaluated it not only on highway and n-chain, but this synthetic MDP. We have also evaluated it on this continuous control tasks like cut pole, or I think we have also done on this mountain car. Yeah, so we have done it for mainly this kind of environment, the OpenAI gym environment that you get easily for continuous control. Yeah. And in all those cases, actually, we see less number of falls, better risk-sensitive performance.
Cool.
Actually, on that topic, you mentioned continuous action spaces, or did I hear incorrectly? So how would your Sentinel model work in continuous spaces? Because if I understood it correctly, you had these distribution estimators. So if you have a continuous, is it one distribution per action, or what does this? How does the distribution look like? The estimators.
So this distribution estimators always can be extended to. So most of the experiments we have done obviously on discrete action, as you have suspected, that's true. That goes easy. But if we have this continuous space of actions, we can do something like a fitted queue iteration, where rather than considering this, how can I say, this continuous space of actions, you consider lower dimensional representation of that, and you only care about a certain point or certain sampled point of actions for which we want to evaluate, rather than evaluating it for like whole set of actions altogether. Obviously, there can be an error from that due to this present structure, but it would be an interesting thing to extend this to proper continuous action space. Because there can be this error due to discretization of these actions or like how we are using it.
Interesting. Thank you.
Thank you.
I guess you're using some function approximation for these distributions, right? Yeah. So I mean, I guess you could, instead of just parameterizing them over the states, you could parameterize them over the state in action. Argmax is a bit trickier, but it should also be doable, right? It should work maybe a bit more.
It will be a bit more trickier.
Yeah, I think the argmax thing, you'd probably have to do some kind of local search, which is a bit of a pain in the ass, but it should probably.
Exactly. That's the problem, right? Yeah, that's the problem with this kind of lower dimensional or functional approximation of these actions or like states. If we want to use it, you have to do some kind of local search, linear line search. But another thing that can be interestingly done. Carry on.
No, I was just thinking if you had like a fairly simple space on the dependency on the action, you could probably find a analytic solution to it. But as you were saying, if you have some kind of linear representation, but that's probably not very desirable.
Exactly. But another thing that will be interesting to see is the whole point of this work was to prove that this composite risk is a better quantification if you can estimate it well. You can develop a nice estimator of this very simply without distribution assumptions. And if you use it, it leads to safer performances. But now the question is like we have used Q-learning or fitted Q iteration, which is like, like very naive or simple coming from the reinforcement learning point of view. You can use policy gradients if you want to use on continuous action, for example. And you can find out these risk measures or estimate them corresponding like a policy gradient format. So that can be done, and I think there are open things to be done in here. But that was not the main point we wanted to convey. So we didn't focus much or improve much in that part.
Okay. Do we have one last question? Otherwise, I think we'll thank Debabrota for this nice talk, and we'll take a summer break, and then we'll reconvene August 26th with a more applied talk, perhaps by Björn Gambeck on social media analysis and hate speech detection. So thank you, Debabrota.
Thank you, Olaf, and thank you everyone in RISE for inviting me. And thank you for the virtual class.